So after my last video, you may be asking the question, why even do gamma rays in the first place? You may be thinking, my eyes have served me well for a long time. Why do I need to look at things I can't even see? So remember when I said before that gamma rays were the fastest moving particles? Well, I have a bit of a confession to make. That's probably not entirely true in the sense that you think of it. It's true, but it's not true in terms of speed, you see. See, photons are described in terms of two things, wavelength and frequency. And this is a lot of physics terms, but let's just bear with me. So imagine I'm standing here and I'm watching a cat parade, because that's what I do in my free time. And cats are walking by in front of me. Now, the frequency would be the number of cats that move by me per minute. But think about it. The same number of cats could be moving by, but what if I'm counting the distance between their tails? Now, if you have a long cat or a short cat, the same number of cats can be moving by for each minute, but the difference between the tails would be much different. So this is just like, the speed is constant. The speed of light, which is what we're looking at, is 3 times 10 to the 8 meters per second. It's a lot. You can't change that. But let's consider how the wavelength and frequency could be different, even if the speed of light is the same. So the speed of light is dictated by an equation. In this equation, the speed of light equals frequency times wavelength. So remember, the speed of light is a constant, but frequency and wavelength can definitely change. Because remember stuff like 3 times 6, but also 2 times 9 both equal 18. There's more than one way. Now I'm going to show you my sneaky trick that makes gamma rays awesome. So the speed of light equals the same, but the energy of photon, which remember is just a bit of light, can be different. So hc, this is just physics stuff, it's just a number, is divided by the wavelength. So small wavelength equals a really high energy, even if the speed of all light is the same. So now imagine you have 2 cats, and one of these cats is a sleepy cat. He doesn't have much energy. And the other cat is a really energetic cat. So now both these cats are walking towards a wall. Now imagine if the energetic cat can walk through walls because he has so much energy, and the sleepy cat can't. Hey, it's not a perfect metaphor, just bear with me. Again, I'm making an imperfect metaphor for photons, which remember, are just bits of light. So, imagine again, you're standing on the Earth, and you're observing the stars with your normal optical telescope. And you're trying to see a star, but unfortunately there's a cloud in the way, and think about it, if there's a cloud in the way, you can't see what's behind it. But that's just with you looking with your eyes. Now, imagine there's like a black hole behind it or something that could accelerate particles to gamma ray energies. A satellite like Fermi could pick that up and you could know what was behind the cloud, even if you can't see with your own eyes. So that's just one of the reasons why looking at gamma ray sky is much different than looking at the optical sky, because you can see behind the clouds. Also, think about it. How did that black hole give those photons that much energy in the first place? These are the questions I ask myself every day on the job, and I think it's pretty cool.